Yeah, it's fine.
Okay. Right. So welcome back, everyone. So today, the first talk of the session is by Terrence George from Michigan, and he'll talk about dimers and Beauville integrable systems.
Yeah, thank you. Yeah, thanks for the invitation. It's nice to be here in ICTS in person. So this talk is based on two projects that are closely related. The first one is joint work with Alexander Goncharov and Richard Kenyon. And the second one is with Giovanni Inchiostro. So the plan is as follows. So starting with a convex polygon in the plane that has a convex lattice polygon. So what this means is all the vertices of this polygon are lattice points, like this polygon over there. There are two ways to get an integrable system out of it. So the first construction is from combinatorics. The first construction is from combinatorics, and it's due to Goncharov and Kenyon. And this proceeds via what is called the planar dimer model. So this is a certain model in statistical mechanics, and it produces something that's called a cluster integrable system. The second construction is, so from a polygon, you can construct a projective toric surface. So in this case, you get P2. And there is a construction of Beauville from 91, which produces an integrable system on this toric surface or on some space that is associated to this toric surface. And there is a map between these two integrable systems. So this is called the spectral transform. And this kind of map is very well known in the study of integrable systems. So this was originally defined by Kenyon and Okounkov for reasons that are unrelated to the integrable system. They were interested in some other problem. So this map actually predates the integrable system. And so there is a map between these two integrable systems. And there is an inverse construction due to Vladimir Falk. And the project with Rick and Sasha, with Goncharov and Kenyon, is to give an alternate construction of this inverse map. So of course, if you have two inverse maps, they must be the same. So I'll tell you in what sense this is a different construction of this inverse map. And the second project with Giovanni is to show that the spectral transform is actually an isomorphism of integrable systems. So you have a map between these two, say, algebraic varieties. And the second statement is that it preserves all the structure of the integrable system. Okay, so the plan is to first talk about the dimer integrable system, the one from combinatorics, and then I'll describe the Beauville integrable system, and then I'll describe the map and say why these are the same. So the planar dimer model is a very simple model in statistical mechanics. The setting is as follows. You have a bipartite graph in the plane, such as this graph over here. So bipartite means that all of its vertices are colored in two colors, so say black and white, and all the edges are between black vertices and white vertices. So you don't have any black edges or white edges. And we assume that we have the same number of black and white vertices. And there is some additional data. So on each edge, you associate to each edge a non-zero complex number or a positive real number. So if you're doing probability or statistical mechanics, you want to choose positive real numbers for each of the edges, but we will be doing some algebraic things. So we will usually think of C star weights on these edges. Okay, so a dimer cover is the same thing as a perfect matching in graph theory. So it's a subset of the edges of this graph such that every vertex of the graph is used exactly once. So this here is an example of a dimer cover. So if you look at each of the vertices, there is exactly one red edge that is incident to it. And say again? No, the graph is assumed to be bipartite. So a lot of these things work even if the graph is not bipartite, but it's nicest when the graph is bipartite. Are there other questions? Okay, so once you have a dimer cover, because we have weights on the edges, we can associate a weight to the dimer cover in sort of the standard way. You assign the weight of the dimer cover to be the product of weights of all edges that appear in it. So the planar dimer model usually refers to the study of a certain probability measure on the set of dimer covers called the Boltzmann probability measure. And it's defined as follows. So first, we need to define what is called the partition function, which is some sort of normalization constant that appears in the probability measure. And it's the sum of weights of all dimer covers. So if you look at this graph over here, there are exactly 3 dimer covers, these 3 that are shown over here. Shown below them are the weights of the dimer covers, and the partition function is the sum of weights of these dimer covers. And the Boltzmann probability measure assigns to a dimer cover a probability which is proportional to its weight. So once you normalize by this partition function z, the probability is going to add up to 1. So for example, this dimer cover over here has probability. So its weight is A times C times F. So its probability is going to be A times C times F divided by Z, where Z is this quantity. Oh, like why we are multiplying the weights. So usually you want to think of the weights as telling you how much energy it takes to create a dimer at that site. So you should think of the weight as like e raised to minus energy over kT. And the fact that these multiply corresponds to the fact that the energies add up. Like if you create a dimer that uses 3 edges, the total energy is the sum. But because it's appearing in the exponent, it multiplies. So the amazing fact, which is true for planar graphs and usually for graphs embedded on topological surfaces, is that you can compute the partition function for dimer covers using the determinant of a certain matrix. So this is sort of analogous to the matrix tree theorem. So here's how you do it. So we are going to write down what is called the Kasteleyn matrix. So this was invented by the physicist Kasteleyn in the 1960s. So here's how it goes. So the Kasteleyn matrix is essentially a weighted adjacency matrix of the graph, except there are some signs in it. So here, so you need to assign some signs to some of these edge weights. And the way you assign these signs is by the following rule. So for every face in the graph, you want the product of signs of edges around this face to be minus 1 to the power number of edges in the face divided by 2 plus 1. So if you have a square face like this, then you want the product of signs to be minus 1. If you have a hexagonal face, you want plus 1. If you have an octagonal face, you want minus 1, and so on. So yeah, it depends on the embedding. So this requires a planar embedding of the graph. Yeah. Right. So here is one way to choose. So there's a lot of choice for how you can choose these signs. So here is one way to choose the signs for this graph. So if I put a minus here and a minus here, both these square faces now have a product minus 1. So this is a valid Kasteleyn sign. But you could instead just put a minus sign at this D and you would still satisfy the sign condition. So there are many choices, but it doesn't matter. So once you put these signs, you can write down a bipartite adjacency matrix. So the entry that corresponds to, so the columns are indexed by black vertices, the rows are indexed by white vertices, and the entry in column B1, row W1, is going to be the weight of the edge between B1 and W1. So it's just the adjacency matrix, but you put the weight instead of ones. So similarly, B2, W1. So B2 is here and W1 is there, and there is this edge with weight minus B. So you put a minus B in that entry. And yeah, this is only for planar graphs. This construction extends to graphs embedded on surfaces, but it's more complicated. And we will actually look at graphs on the torus. That's where we are going. Yeah. Oh, okay, maybe. Yeah. Are there other questions? Yes. So if you choose all the weights to be 1, right. So the theorem is that the determinant of this matrix gives you the partition function for dimer covers. So if you choose all the weights to be 1 and find the determinant of this matrix, it's going to give you exactly the number of dimer covers. So the theorem of Kasteleyn is that if you take this Kasteleyn matrix and find its determinant, you're going to get the partition function for dimer covers. So the non-trivial fact is that there are no minus signs appearing in any of these. So it's clear that you're going to get a weighted sum of dimer covers with possibly signs in there. And the fact that you choose this Kasteleyn sign condition is going to guarantee that you only have a plus. it's not planar, right? Yeah, this is only for planar bipartite graphs. So this is why right, everything works for the diamond model. It's because of this fact that there is this determinant that you can write down that gives you the partition function. Okay, so yeah, like to define the Kasteleyn sign condition, you're using the notion of faces, which already requires planarity. Okay, so the cluster integrable system, the one associated to the diamond model, so it's sort of strange. It lives really on the space of weights that you assign to the graph. So the goal is to define what is the right space of weights that you want to put on the graph. So we said that weights are some non-zero complex numbers that you assign to each of the edges, but there is a certain gauge condition that you need to mod out by. So here is the observation. So the probability of having this dimer cover with these weights is this expression over here that we saw. Now, if we take every edge that is incident to any vertex and we multiply the weights of all those edges by the same constant lambda, then because every dimer cover is going to have exactly one edge that is incident to this vertex, the weight of every dimer cover is going to get multiplied by lambda. So if you look at the probability, since you're normalizing by the partition function, the lambdas cancel out and the probability is unchanged. So the probability does not depend on changing the weights in this way. So we are going to define the space of weights on this graph as these edge weights modulo these gauge transformations, where you modify the weights in this way. Yeah. So you want to mod out by such transformations at every vertex, right? Yeah. So the space on which the integrable system lives is the space of edge weights modulo gauge equivalence like this. So what is this space and what are coordinates on this space? So we need to find some gauge invariant functions on this space. So here's the observation. If you take any cycle in the graph, so for example, the boundary of this face, and you take the alternating product of edge weights around that cycle. So say we are going counterclockwise around this face, and we take the alternating product such that if you are going from black to white, then you put the weight in the numerator. So as you go around the cycle, the alternating product is A times 1 over B times C times 1 over D. So AC over BD. This quantity is going to be invariant under gauge transformations because we are taking an alternating product. So this vertex is used by exactly A and B. And since one of them appears in the numerator and the other one's in the denominator, when you do a gauge transformation, it doesn't change this quantity. X f0 is also defined in the same way, except I think we are going, the outer face is oriented like this. Let's see, so yeah, so we are going this way around the face. So it's B divided by A times E divided by F times G divided by C. Yeah, it's bipartite, right? Yeah. So this, yeah, all of this requires the bipartiteness. So really you have such an XL associated to every cycle, every oriented cycle. So we are just defining the boundary of a face to be oriented counterclockwise. Oh, it doesn't matter where you start, right? Like if I started here instead, I would be like 1 over B times C times 1 over D times A.
No. It has to start with the black
Yeah.
It doesn't matter where you start
Or yeah, another way to say this is, say we orient all the edges from black to white, and then we go around any loop. And if it's consistent with the orientation, it's in the numerator. Otherwise, it's in the denominator. So this function, which takes a weight and outputs this number, which is the alternating product, is called the monodromy around that cycle. So another way to think of the space of weights is that it's the cohomology of the graph with coefficients in C star, because if you look at edge weights, so cellular cohomology, so if you think of edge weights, that's the same thing as a one cocycle on the graph. And modding out gauge equivalence is the same thing as modding out coboundaries. So another way to think of this space is as the cohomology of the graph, and then you see that you have relations among the XLs that come from relations among cycles on the graph. So for example, here you have this relation that the product of xf0, xf1, xf2 is 1, which comes from the fact that if you take the face oriented counterclockwise like this, the space oriented counterclockwise like this, and the outer face oriented in this way, then the sum of these three is 0 in homology. And that gives you this relation in cohomology. Yeah. Yeah, we are. Yeah. Okay, any? Yeah, it's also, the character variety with values in C star. That's right. So there are many ways to think of this space. It's the space of C star local systems. Yeah, so because it's C star, yeah, the trace is just, it's almost, Yeah, so people do study like SL2 or other weights, and so those correspond to some more general combinatorial objects, not dimers, but something more complicated. But yeah, there's a lot of interest in this kind of stuff. Yeah, they assign matrices as edge weights, and then they take products of matrices. One of the what? Yeah, that's right. So, right, the term X is because this is supposed to be a chart for a cluster variety. And that's right. So yeah, this is a chart for a cluster variety. It's the Fock constant of X cluster variety. Are there other questions? Yeah. So in this case, these two faces, F1 and F2, their boundaries generate the homology of the graph, and this relation says that once you know these two, then everything is determined. So there's a two-dimensional space of weights, and that's the C star coefficients. Okay, so the actual setting of the cluster integrable system is not bipartite graphs on the plane, but rather bipartite graphs on the torus, where there is a very similar theory. So here is why you might want to think of bipartite graphs in the torus if you're interested in statistical mechanics. So you're interested in letting the size of the graph become very large and looking at questions like, what does a random dimer cover look like? So in the limit, you have a bipartite graph that is infinite on the plane. And this is intractable unless you put some kind of periodicity conditions on the graph. So you would usually assume that the weights are periodic under translations in both directions in the plane. And then if you mod out by the group of translations, you get a bipartite graph on a torus. So this is why people were originally interested in studying bipartite graphs on the torus. So the setting is as follows. So we have a torus, which you can think of as being glued from a parallelogram. So you take this parallelogram, you glue the top and the bottom, and you glue the left and the right sides, and then you get a torus. And this is a graph that is embedded on a torus. So for example, this edge that starts over here and hits this side of the parallelogram is the same edge that comes out over here. So it's the same setting, except now the graph is not planar anymore, it's embedded on a torus. So in this setting, there is a version of the Kasteleyn matrix, which is due to Kenyon-Okounkov-Sheffield. But there are some differences. So here, the main difference is the following. So every time you have an edge that crosses one of the sides of this fundamental domain, if it's crossing, say, the right side, then you're going to put an additional factor of Z. And similarly, if you have an edge that crosses this horizontal side of the fundamental domain, you're going to include an additional factor of W. So this edge over here, it has a weight, which is B11, and you're going to multiply that weight by an additional factor of Z. So we write down a Kasteleyn matrix, which now depends on two formal variables Z and W. It's the same adjacency matrix. So there is no Kasteleyn sign condition because all your faces are hexagons. So all the signs should be +1. So you don't need to put any signs in there. It's the same adjacency matrix, but let's look at the entry, for example, B12, W11. So B12 is this vertex over here, and W11 is this vertex over here. There is an edge that, this edge that goes between them. So because it crosses the boundary of the fundamental domain, you have this additional factor of W. So you have C11 times W. But otherwise, it's the same as the Kasteleyn matrix we defined for planar graphs. Oh, no, these are just the names of the word. So the black labels are the names of the vertices. The red numbers are the weights on the edges. Any other questions about this? Okay. Yeah. So then you can take the determinant of this slightly generalized Kasteleyn matrix. Yeah. Yeah, this.
That's all the data. Goes around in this direction with every power of Z.
Yeah, so we'll see soon what the Z and W mean. It's no, it's a variable. So you. Yeah, it's going to keep track of some information about how many times the dimer cover winds around the torus. So I'll say precisely what it keeps track of soon. So you can take the determinant of this Kasteleyn matrix, and it gives you a polynomial in Z and W now, which is called the characteristic polynomial. So the Newton polygon of this polynomial is going to be a convex lattice polygon. And this is the lattice polygon that I started the talk by saying that you have a cluster integrable system associated to a lattice polygon. The way we arrived at it is the other way around. We started with a bipartite graph and we produced a polygon. So this construction is sort of invertible. If you start with any polygon, there is a way to construct a family of graphs on the torus whose Newton polygon is the polygon you started with. So these graphs should be thought of as charts for a cluster variety, and there are some moves that relate these graphs, which are mutations in some cluster algebra. Yeah, this is not at all obvious that for any polygon there is a class of graphs whose Newton polygon is this. Right? It's a theorem of Goncharov and Kenyon that you can go back. Say again? Oh yeah, so here we are sort of dealing with a very special example, which is this honeycomb lattice. In general, if you have a general graph, so somehow we didn't have factors of 1 over Z or 1 over W. This is because all our edges are kind of oriented in the same way. But if you had an edge that was oriented in the opposite way, so suppose the white vertex was here, then you would pick up a factor of 1 over W. So in general, this matrix is going to be Laurent polynomial valued, and so is this. Okay, so if you look at this polynomial, you can see that these entries, these numbers, these terms over here, they are enumerating dimer covers, but you lose the fact that all the signs were positive, and you have this additional Z and W in there. So there is a way to make everything positive, but we don't need that. And also there's a good reason to not make things positive. Like these polynomials are very special, as we'll see. Okay, so what do the factors of Z and W keep track of? So let's choose this dimer cover, the one that corresponds to this, as a sort of reference dimer cover. So all the blue edges are a kind of reference dimer cover. And then if you take any other dimer cover or any other term in this polynomial over here, it's going to be a bunch of edges. So in this case, it's all these green edges. and you superpose it on top of the blue dimer cover, then because a dimer cover uses every vertex exactly once, when you superpose two dimer covers, it uses every vertex exactly twice. So this is going to be a disjoint union of loops. So for example, this is a loop of length 2, so it's a kind of degenerate loop. And this is a more interesting loop over here. And the W over here is keeping track of the fact that this loop winds around the torus one time vertically. So this is sort of a generating function for dimer covers, where each dimer cover is weighted according to how many times it winds around the torus. Okay. But we are not going to think of it as a generating function. We want to think of it as an actual polynomial. So once these weights are C star valued, this is an actual polynomial. So we are going to look at the curve given by the vanishing of this polynomial. So because the Newton polygon of this curve is the triangle, the natural way to, so this curve a priori lives inside the torus, but you can naturally compactify it to get something that lives in P2. So this compact curve that you get by taking the closure inside P2 is called the spectral curve. And notice that the construction of the Kasteleyn matrix required choosing edge weights. Also, the characteristic polynomial depends on edge weights, but the spectral curve is something that is actually gauge invariant, because if you do gauge transformations, then you're multiplying the weight of every dimer cover by a constant. So the vanishing locus of this polynomial is still the same. So you do get a gauge invariant object at the end, although the process you took to get there was not gauge invariant. Okay, so because this conference is about real algebraic geometry, I thought I should mention what this means in terms of real algebraic geometry. So there is a amazing theorem of Kenyon-Okounkov-Sheffield that if you choose all your edge weights to be positive, which is what you do when you're studying probability, then the spectral curve is a very special type of real algebraic curve, which is called a simple Harnack curve. So in one of the earlier talks, we saw another type of real algebraic curve, which is called the Vinnikov curve in the talk on hives. And so real algebraic curves, unlike complex algebraic curves, have interesting topology. They don't look all the same. So the kind of curves we saw were like this, where all the connected components, which are called ovals, are nested one inside the other. Simple Harnack curves have sort of the other extreme of topology. There is one big oval, which is the only one that intersects the toric divisor, and all the other ovals are kind of spread out, and none of them are nested. So it's another topology for this real algebraic curve. And it turns out that more is true. Every simple Harnack curve arises as a spectral curve of a dimer model. So the spectral curves of dimer models are exactly the same, the class of simple Harnack curves. And this has sort of amazing consequences for the probability, for the statistical mechanics of this model. Oh yeah, I mean, other than this outer oval, which is there is one oval which inside which you might have things. Yeah, that is okay. Yeah, there is one big oval that intersects the toric boundary, and then all the other ones are not nested. Yeah. Yeah. Say again. Oh, Higgs bundles. No, I think it's So this class of integrable systems contains many other integrable systems, but I think it's not the same as the Higgs. That's an unrelated integrable system. Like I don't think there is a connection, or at least that I know of, between these two. No, you can take all the weights to be 1 and it will give you some curve, right?
Generated by the axis
Uh-huh. Oh, right. So yeah, what you can do is you can take, say, this dimer cover over here and divide the whole polynomial by that. And then once you do that, everything becomes loops, as in products of loops. And then, yeah, you can write it in terms of the x coordinates, right? So yeah, then you get an actual gauge invariant expression. Yeah. Right. So, right, the spectral curve is still the same once you divide by this, right? So yeah, it's just a gauge invariant way of writing the polynomial, but the curve is, yeah, the same. Are there other questions? Okay. Okay, so the space of weights is where the integrable system is going to live. So an integrable system, on the next slide, I'll say a bit about what an integrable system is. But one of the things it has is a Poisson structure. So we need to put a Poisson structure on the space of weights. So this actually comes for free because the space of weights is a cluster variety, and every cluster variety has a canonical Poisson structure, which is due to Gekhtman-Shapiro and Weinstein. And so this is only this is not a complete definition, but here is a partial definition of what this Poisson structure is. So we saw that regular functions on the space of weights were given by these XLs, where L is a loop, these monodromies around loops. So to define the Poisson structure, I can tell you what the Poisson bracket between two of these regular functions is, and then extend it by linearity. So say we have two faces. I want to tell you what the Poisson bracket between these two is. So if there is a directed graph associated to this bipartite graph, which is called a quiver in cluster algebra terminology. And it's essentially the dual graph of this bipartite graph. So notice that every edge has a black endpoint and a white endpoint. So you can define a directed edge so that the black endpoint is on the left, on the right. So you direct all edges such that the black endpoint is on the right. And this gives you a directed dual graph of this bipartite graph. And that's the quiver of the underlying cluster algebra. And the cluster Poisson structure, the canonical Poisson structure, is defined as follows. So it's log canonical. So the Poisson bracket between xf1 and xf2 is given by the number of directed edges there are from f1 to f2 minus the number of directed edges there are backwards times the product of the two functions. So it has this very simple combinatorial description. But why is this not a complete definition? This is because these the boundaries of faces do not generate the homology of the graph because the graph is on a torus. So you also need cycles that wind around the torus. And I haven't told you what the Poisson bracket is between these functions that are monodromies of cycles winding around the torus. But that's a little bit more complicated to define. So this is an approximate definition, which would be, yeah, which is the monodromy of, or the alternating product of weights around that face. There is nothing special about the torus. It's just that all the dimensions match up in the torus and you get an integrable system. No, these things you can do. You can put bipartite graphs. You have a quiver. All these things are, yeah, they work just the same way. Yeah. What is special is you only have the integrable system on the torus. Yeah. Oh, yeah. Yeah, I should really say number of edges going forwards minus the number of edges going backwards. Yeah, this is. Yeah. Oh, yeah, there are two edges actually. Yeah. There is this one and this one. Yeah, then it's 0.
It's just edges, not paths.
Yeah, it's just edges. Yeah, so it turns out it's compatible with the relations, but it's probably not obvious from this, right? Like the faces always satisfy a relation that the sum of all the faces is 1 in homology. So the product of all these x F's is going to be 1. And this Poisson structure is like it works well when you quotient by this relation. Yeah. Yeah. Yeah, there is a better way of defining it, but it's more technical, right? Where it's obvious that everything is well defined. Oh, so these are just any faces. So take any face F1 and any face F2. So like you could take this face and this face. These are just indexing faces. Yeah, face of the underlying graph, which are the vertices of the dual graph. So that's so you have edges between them. Okay, so here is a vague idea of what an integrable system is. So you're in the setting of classical mechanics in the Hamiltonian formulation. So you have a symplectic manifold. So a manifold equipped with a closed non-degenerate 2 form. And an integrable system is a map to a base that is a Lagrangian fibration, which means that the dimension of each fiber is half the dimension of the space. And if you restrict the symplectic form to each fiber, it's going to vanish identically. So the functions on the base are usually called commuting Hamiltonians. Yeah, that's what vaguely an integrable system is. So another way to think of this is it's a space in classical mechanics which has as much conserved quantities as possible. So the reason it's called integrable is in this case you can explicitly integrate the equations of motion because you have so many conserved quantities. So the setting that we are going to deal with is a little bit more general, but it's almost the same as this one, except that in general, we are going to have a Poisson manifold, and the Poisson structure might be degenerate, so it's not automatically dual to a symplectic structure. But we have a fibration like this, where in the base, you also have these extra functions called Casimirs, which are functions that commute with everybody with respect to the Poisson structure. So these are always invariant. So if you pass to like the level set of these Casimir functions, then you get an honest symplectic manifold, and it's the same definition here. So the only difference is there are some extra functions that don't really do anything. Wait, say again. Oh, so the notion of Lagrangian is once you pass to the level sets of these Casimirs, then it's a Lagrangian fibration. Yeah. So the level sets of these Casimirs are symplectic manifolds, and there it's the same definition of this one. Okay, so that's roughly what an integrable system is. So the theorem of Goncharov and Kenyon is that this map, which assigns to the space of edge weights the spectral curve, is an integrable system. So this with its canonical cluster Poisson structure is an integrable system. Only for the torus. So in general, so here we were dealing with the honeycomb lattice, which is sort of the simplest example where you don't have any mutations. In general, if you start with an arbitrary polygon, you should replace this X gamma by an appropriate cluster variety. So these X gammas will be like affine charts for this cluster variety. And in general, P2 will be replaced by the appropriate toric surface. And then the same statement holds that this is an integrable system. So I think the way to think of it is it's a system with lots of invariants, like lots of, right. So what you usually do in classical mechanics is you have some function called the Hamiltonian, and then you try to figure out how the system is evolving by like the partial derivative of any function with respect to time is given by the Poisson bracket with the Hamiltonian. So if you have something that commutes with the Hamiltonian, as in h comma, that function is the Poisson bracket of this is 0, then that function is going to be invariant under the dynamics. And so you're always going to stay on a level set of that function. So because you have a maximal number of invariant functions, you can keep passing to level sets and get a smaller dimensional problem. So integrable systems are the ones where you have as many conserved quantities as possible, so you can pass to a really simple. I think that's the impression that I have. So the symplectic leaves are a bit strange, but I can tell you what they are. So there are some special paths in the graph which go zigzag. So for example, this path that goes zigzag like this. So the monodromies of around these zigzag paths are going to be Casimirs for this Poisson bracket. And once you fix the monodromies around every zigzag path, that gives you the symplectic leaf. Oh, there is another description of this Poisson structure which sort of tells you why this has to be the symplectic leaf. So, but it's a little bit technical, but I can try to tell you what it is very vaguely. So what you do is you fatten this graph and get a ribbon graph out of it. And then you cut each edge. So each edge is going to be a ribbon. You cut it and you glue it with a twist. So you twist the ribbon once and you glue it back. So this process, if you do it for every edge, is going to give you the same graph embedded on some other surface, no longer the torus. And the Poisson structure is defined in terms of the intersection form on that new surface. And it turns out that this construction interchanges faces and zigzag paths. So what used to be zigzag paths becomes faces in the new ribbon graph. So intersection form of those zigzag paths with everybody is 0. And that's why they are the Casimirs. So that's really the right way to define this Poisson structure, but it's a very strange definition when you see it. Yeah, that's right. It's not integrable, but the cluster variety is something that is well studied. It's the Grassmannian. This is Posnikov's theory of positroid cells and things like this. So if you study dimer model in a disk, the cluster variety is exactly that theory. Yeah, no, I think it'll be like a very similar description in terms of zigzag paths. Yeah.
So the question is about graphs embedded on the sphere.
On the disk, or yeah, on the plane, yeah. Yeah.
So there the corresponding system is not integrable.
Yeah, it is not integrable. Yeah. So somehow in the torus, so for it to be integrable, you want the dimension to match up. Like you want the dimension of the base to be the same. I think this only happens for the torus. I think. Oh yeah, there is maybe a better way to say what the symplectic leaves are, which is if you look at these degree D curves, they're going to pass through some points at infinity of the toric surface. The symplectic leaves or the Casimirs are so basically you're fixing the curves at the boundary. So the symplectic leaves correspond to moving the curves such that you fix the curves at infinity. And we'll see that this is also how the symplectic leaf of the Beauville system is defined. So yeah, the next slide is about the fibers. Right, so we have this fibration. So natural question is, what are the fibers? What do they look like? So this is where the map of Kenyon and Okounkov called the spectral transform comes into the picture. So we got the curve as the determinant of a matrix called the Kasteleyn matrix. So if you also take the cokernel of the Kasteleyn matrix, this is going to define some line bundle of degree G over the curve. So it's not too hard to see that it has to be a line bundle supported on the curve, but the degree is harder to calculate. But always the cokernel is a line bundle of the appropriate degree. So if you define the following map, where you start with a weight and you construct the spectral curve and this line bundle which is on the spectral curve, this gives you a reparametrization of the space. So a theorem of Fock says that this spectral transform is a birational map. So if you start with a spectral curve and a degree G line bundle, you can reconstruct weights on the graph from it. And from this description, it's easy to see what the fibers are. Right? The fibers are going to be the space of line bundles of degree G on the curve. So this is the Picard group, and it's going to be a torus. So the fibration actually looks like this. And this is a general feature for integrable systems. It's a theorem that if you have a fiber that is compact, it has to be a torus. And in this case, the torus is the Picard group. Oh yeah, I forgot to say what G is. G is the genus of the curve. That's right. or it's the number of interior lattice points in the polygon. Okay. Yeah. Are there any other questions before we move on? Say again? Oh, so the Kasteleyn matrix is a Laurent polynomial valued matrix. So you can think of it as a map of locally free sheaves on the torus, and you take the co-kernel as a sheaf. Oh, wait, say again? Yeah. Yeah, so yeah, that's something that I didn't say, right? There is something subtle going on here, which you're right. A priori, the Kasteleyn matrix is defined on the torus, but the spectral curve and this line bundle are defined on the compactification. So you need to somehow extend the Kasteleyn matrix to all of P2, and this is a bit tricky. So there is a way to extend it to a map of locally free sheaves on P2, but it's a little bit complicated to say how to do it. Are there other questions? Okay, so what's the Beauville integrable system, the other integrable system that we talked about? So it's a very simple system. So you start with G, where G is the number of interior points in the polygon, or the genus of a degree D curve. So you start with those many generic points in P2, and you fix also 3D minus 1 generic points on the boundary. So you fix D points here, and say you fix D minus 1 points here. Then we saw last week in this context of Gromov-Witten invariance that there's going to be a curve that goes through all of these points, and generically there's going to be a unique curve that goes through all of these points. So this 3D minus 1 looks a little bit strange. It looks a little bit not symmetric, because if you have a degree D curve, it's actually going to go through 3D points at infinity. But there is going to be a condition among these points at infinity. So you fix 3D minus 1, and the last one is fixed. Okay, so this is the space on which the Beauville system lives. It lives on this choice of points. And so this construction of taking the unique curve through these points gives you a fibration over here. And with this Poisson structure over here, Beauville showed that this is an integrable system. So the fiber over a curve is all possible ways in which you can choose G points that live on the curve. And it's a theorem of Riemann that G points on the curve is birational to the Picard group of pic G. So this is the same description as the space we had earlier. It's the space of all choices of G points in P2 and 3D minus 1 points on the toric boundary. And again, the symplectic leaves here are you fix the points at the boundary and you vary the G points inside the torus. Okay, so this again works for any toric surface. So this Poisson structure is also a very natural Poisson structure. So if you look at the dual symplectic form, it's just the D log form on the toric surface. Okay, so this is Beauville's integrable system, and it lives on the other side of the spectral transform. And the theorem with Goncharov and Kenyon is the following. So we have the space of weights. We have a spectral transform, which gives you a curve and a line bundle. And that space is the same as choosing G points in P2 and 3D minus 1 points at infinity, because if you know these points, then you can reconstruct the spectral curve as the unique curve through these points. And you can reconstruct the line bundle as just O of that divisor of G points. So in this way, you get back the curve and the line bundle. And this is invertible. If you have the line bundle of degree G and it's generic, then it has a unique section that is holomorphic. And you take the divisor of that unique section and you recover the divisor. So these spaces are really the same. And the construction of Fock uses this as the domain, and it involves theta functions on the Jacobian and things like this. So it involves some transcendental functions. The construction that we have is really the same construction in some sense, but somehow this map involves theta functions and this one involves theta functions, but they kind of cancel out. And the map we have, it's a rational map. It just involves rational functions in this data and no theta functions or things like this. So it has that advantage of being somehow more explicit to work with, but it's theoretically less nice than Fox construction. Like Fox construction is very neat. Okay, so that's the one theorem. And the other theorem with Giovanni is, so now we have this space, which is the phase space of the cluster integrable system. And we have this other space, and we have a map between these spaces that is birational. So it's natural to ask, does this birational map preserve all the structure of the integrable system? Is it mapping the integrable system on one side to the integrable system on the other side? And that's the theorem that, so some things are obvious to see. So the fibration we had over here looks like this, and the fibration we had over here looks like this, and the base is exactly the same. It's the space of degree D curves. And the spectral transform maps this side to this side. So it's clear that the Hamiltonians on this side go to the Hamiltonians on this side. The only thing that really needs to be checked is that the Poisson structure over here, which is this cluster Poisson structure, maps to the cluster Poisson structure, maps to this Beauville Poisson structure on this side. And so that's the theorem with Giovanni, that indeed this map is Poisson. It does take the Poisson structure to the. Okay, so that's all I wanted to say. So thank you.
Thank you. Nice talk and answering lots and lots of questions, but I'm sure there are more.
Wait, say again. Let's. Right, I did. Yeah. So is there a way to write this on the cluster side? Oh, yeah, right. I mean, if you write it, it's going to be some slightly horrible, like big expression. Right. Yeah, this is somehow, it's more compact, but that's right. Yeah, so I guess it's saying that that slightly complicated looking Poisson structure becomes this one. But I would say that this one is really not that bad either, because it's just the intersection pairing, it's just the intersection pairing on some surface, which is, yeah, so yeah, it's like if you try to write down the bivector field, it's a big expression, but the Poisson structure itself is very nice.
So just going back to the question I asked at the beginning of the talk, if I replace abelian weights with, say, SL2 or SL3 or something.
Say again, it's a little.
If I replace the abelian weights with the simplest non-abelian weights, maybe like SL2, say, or SL3, what can what can one say in that case?
Oh, so
what happens?
Yeah, so Rick Kenyon has actually been working on this kind of questions recently. So I think what they see is there is, so instead of dimers, there is a more complicated combinatorial object, which is called a web. And you can do the same kind of Kasteleyn matrix constructions, except now things live on like the weights become SL2 valued and things like this. But so there is some representation theory in the background that you have to do, but there is a version of Kasteleyn's theorem which says that the determinant enumerates these webs and things like this. Yeah, I think not too much is known about this thing because like this work of Kenyon is very recent. Yeah, but I think it's an interesting question.
So is this work already out, or is it?
Yeah, it's on archive. Oh, the one of Kenyon, right?
Yeah,
yeah, it's on archive. Yeah. So the A variables are a different kind of cluster variable. So they're like right? Yeah. So these are like the X variables and stuff, the A variables. So I think in some cases, like So the surface cluster algebra comes from some kind of triangulation of this, right? So I think there is a way to start with that and draw a bipartite graph such that you have the same cluster algebra. But I don't know if every bipartite graph gives rise to a surface. Like the other way, I don't know. Like if you start with a surface one, I think it is a special case of this. Yeah, so there should be a corresponding A version of all this story, but it's not so well understood. Yeah. This one? Oh, so the fiber is, so if you fix the curve, then you're fixing also the points at infinity. So the only thing that can move are these green points, or like the points. I have a bigger picture. So the only thing that moves are these green points, the G points that you chose over here. So these G points can move around anywhere on the curve. So the fiber is essentially the choice of degree G effective divisor on the curve. Yeah. Yeah, sim G P C. Yeah. Oh, the theta function comes in because so the way Fock constructs his inverse map is okay. So you have the Kasteleyn matrix. So for every which goes between the space of black vertices to the space of white vertices. And then since L is the co-kernel, there is a map from the space of white vertices to L. So, so for every white vertex, you have kind of a section of L. And the way Fock starts his reconstruction is he tries to reconstruct these sections of L, one for every white vertex. And when you want to write down the section of a line bundle, the way you can do it is using theta functions. And then it's actually really nice, his construction. He shows that the Kasteleyn matrix becomes an identity for theta functions called phase identity. So it's equivalent, the fact that, the Kasteleyn matrix somehow equivalent to this phase identity.
Any other questions? Maybe are there questions from the online audience? Please raise your hands and we can try and unmute you. AV team, can you please allow the participants to unmute themselves? Yeah, thanks. You can now unmute yourselves and ask if you have a question. There are only 3 participants. I can see, yeah. I guess there are no more questions. Okay, so then let's thank Terrence for a very nice talk.